Okay, team, we're going to wrap this up with a great example of a practice problem. Actually, it wasn't even a practice problem. It was a homework problem that was issued in AY 20-2. So just a couple years ago, focused on analyzing exergy in a control volume, specifically a gas turbine, comparing two different proposals. So this video, this walkthrough is optional. It will take a bit of time, but I want to give you all the details that we can in terms of analyzing a system using the concept of exergy. Okay, so here's that problem. In short, the idea is that a colleague of yours or one of your teammates came forth and proposed a turbine design that's shown on the left. Let's call that Cadet Williams. And then another one of your friends proposed a separate turbine design with different inlet flow conditions. And let's call that Cadet Sanchez. The two cadets, you can see these inlet conditions here, were governing the design. Cadet Williams ran with a higher mass flow rate, which you can see here, of 1.5 kilograms per second. Cadet Sanchez, on the other hand, designed towards 1 kilogram per second. The exit conditions, you can see at the bottom, are identical. The dead state, or the surrounding conditions around both turbines, is identical. And so you are tasked with analyzing these systems over a variety of basically questions. The first of which is find the rate at which exergy enters the turbine, exergy flow I, for each proposal. Second, part B, is find the rate of exergy destruction, EXD, exergy destruction, or the rate of exergy destruction. Notice that when we talk about rates of anything, we're talking about kilowatts, because it's the rate of something. In this case, the rate at which energy flows. So say kilojoules per second would be a kilowatt. Part C would be using an exergy rate balance, determine the amount of power. W dot IE in this case, expressed in kilowatts. And then last, part D, is find the exergetic efficiency, eta EX, exergetic efficiency, which you will see, expressed in terms of percentage. And then actually, I just said finally for that one, but let's skip over that idea. So we're going to look at part E, which is then saying we're going to compare, jumping down here, we're going to compare the rate at which energy flows into the system and compare that with the rate at which exergy flows into the system, or each of the two comparative systems, and then use that to try to help us explain the performance that we are seeing. The performance that is identified is called out here, and it shows that for Cadet Williams there's a energy flow rate of 1,742 kilowatts flowing into the turbine. And for Cadet Sanchez, there's a rate of energy flow, or power, of 1,515 kilowatts flowing into the turbine. So from those numbers alone, one might expect that Cadet Williams has designed a system that is going to produce more power. So let's figure this out. Okay, so there's a few things that we need to first identify in terms of our MC311 and MC312 problem solving format. So, known. So we are working on a team. So we are working on a team designing a new gas turbine. Designing a new gas turbine. We need to find a few things, right, that we just identified. We need to determine the best design by comparing proposals, by comparing the two proposals. And we're going to do that using the following. So we'll say part A, right? We need to find flow exergy at the inlet of both designs. Part B, we need to find the rate at which exergy is destroyed for both designs. Part C, we need to find the useful work that is produced from both, but in this case we need to do that using an exergy balance. Part D, we need to find the exergetic efficiency of the turbines. And then part E, we need to compare the energy flow rate, or the amount of energy, or the rate at which energy is flowing into the system, versus the rate at which exergy is flowing into the systems. And then we would say, and explain. And explain why those results, or why the results of the comparison are consistent. Why they are consistent with the work that is produced by each of the proposed turbines. Consistent with work IE. So I'm doing this a little bit because of space constraints. Normally my diagram and data would land right below this thing, or right below fine, but I'm going to put it over here on the bottom right for the sake of space. We're going to then identify a handful of assumptions. Take a moment and think about what assumptions you think we should write down here. If you want, even hit the pause button. I'm going to recommend that a number of times while we're walking through this solution set. Okay, so some of these assumptions would be kinetic energy and potential energy are both equal to 0. We would say air is an ideal gas. And we're going to say it's an ideal gas with variable specific heats, right? Variable specific heats, which means that your specific heat at constant pressure or your specific heat at constant volume are not constant, actually. They're varying with temperature. We'd then say the turbine is adiabatic. It's one of the assumptions that we're going to make, and is not called out in this problem. What would have been better, and I think I highlighted this in one of the earlier lecture comments, is if the turbines were drawn with these insulating marks to show that the turbines are insulated and therefore adiabatic. Okay, and then the last thing we're going to say is that the dead state for both systems, as is called out in the diagram, is going to be 0.1 megapascals, and the dead state for temperature is going to be 300 Kelvin. Okay, so that lays out most of the questions that we would have in terms of establishing the problem. One of the actual problem, like the handout that was given to cadets at the time in AY20-2, included this table, Table 2. It also included, or this is Table 1, it also included Table 2, which I'll show you later in this video. So Table 1, I recommend that you try to set up your problems in this way. When you're thinking about systems, it's good for you to very clearly, in a sort of regimented, very disciplined way, establish and remind yourself what all of the properties are for any given state. It's going to allow you to, frankly, in my opinion, succeed. So if you go about this in a very methodical way. So let's look at, say, Cadet Williams. So Cadet Williams has 1.5 kilograms per second, and I'm getting this information from right over here on the left. It has a pressure of 1 megapascal. and then has a temperature of 1100 Kelvin. 1100 Kelvin, as is listed up here in our units. So we're then going to use, I've included some of these tables and such. If you look at the reference manual, your reference manual, if you have a digital or ideally a physical copy of it, you would then go to table 8. So table 8 then lists out all of our properties, or not all of the properties, but ideal gas for assuming air. We have our enthalpy, we have our internal energy U, we have our degrees entropy. This is a convenience property that allows us basically to, it's another property that we can use to help us fix a state. So let's jump down here, and what I wanted to show you was for 1100 Kelvin, we can then swing over here and we can get our enthalpy and we can get our degrees entropy from both the from this single table. So we end up with our enthalpy of roughly 1161 kilojoules per kilogram Kelvin. And we end up with a degrees entropy of just over 3. Now, I'm not going to walk through filling out each one of these cells. I just wanted to point out the process by which we were doing this. And you can scroll down, and I've filled them all out here. If you want, I strongly recommend, actually not if you want, I strongly recommend that you hit the pause button right now on the video, and you go and you confirm every single one of these numbers. If you do not master the tables, I will say this again, if you do not master the tables, you will struggle in a significant way when you hit the WPRs. I cannot say this enough. It happens every single semester. You must practice the tables, and you must practice problem solvings. Please take my word for it. So go confirm these numbers, hit the pause button, confirm the numbers, and then come back to this. Okay. So now, after you have unpaused the pause button, okay, if you go to your reference data card rather, for MC312, what I want to do here before jumping into the analysis is identify the equations that we're going to use throughout this analysis. So for part A, we're going to use a combination of these two equations up here. For part D, the Exergy destruction, we'll use this statement here, which is our dead state temperature times the rate of entropy production. For part C, we'll have our Exergy rate balance. And then for part D, we'll have our exergetic efficiency. Now there are a couple other equations that we will need to utilize. First of which is for variable specific heats. For variable specific heats, we have this equation here for change in entropy for variable specific heat process. Notice that for a constant specific heat process, we have a couple different equations here that could have been used for a constant specific heat. But again, emphasizing we are dealing with variable specific heats across this turbine due to the large temperature change. What is shown here, this is the MC311 RDC. So the MC311 RDC also has a very important equation that we need, which is going to be our entropy production. And in fact, actually, I'm even noticing right now, I called this out right here, but we're going to need a rate. We're going to need a rate. So I placed that B in the wrong location. Please take note. We do not want this equation on the left-hand side. We want a rate of entropy production because we have a control volume, not a closed system. We have a control volume, not a closed system. Things flowing into and out of it. Okay, a couple other things that we need to call out that you're going to need, and I want to highlight them now so we don't have to touch upon them later. But one of the things is going to table 1 in your reference manual. We're going to need the molecular weight for air, 28.97 kilojoules per kilomole. And then on the very back of the reference manual, or if you scroll all the way down to the bottom of the reference manual, you'll find what is the back, and there's at the very bottom there's this fundamental constant statement, and we're going to need this. We're going to need our universal gas constant, 8.314 kilojoules per kilomole Kelvin. Another critical term when we're dealing with ideal gases. Okay, so let's do this practice problem. Let's knock this thing out. So we've got part A. We want to do a rate of flow of exergy. Combining those two equations that I highlighted earlier from your RDC, we can have this statement. Notice that I'm doing it in reference to the dead state. In reference to the dead state, because I'm trying to figure out the amount of exergy that's flowing into the system. I'm not trying to figure out the difference in entropy across the system. I'm trying to figure out the exergy flowing into the system with relation to the dead state. Okay, a couple things, right? We've already said that we're going to neglect kinetic energy. We're going to neglect kinetic energy and potential energy. Now, something to call out here. Let's call this equation 1. And we can then say, therefore, our exergy flow term at the inlet for both designs simplifies to this equation. And our difference in entropies of the inlet to the dead state. But then we must define what that difference in entropies is. And as I said, we need to use those terms for degree entropy, as was called out on our RDCs. So we have our universal gas constant, or an ideal gas divided by the molecular weight, times the natural log, the ratio of our pressures. And this deal is now number 2. Okay, so this was derived. That equation was derived assuming an ideal gas with variable specific heats. With variable specific heats. Okay. And we would say, right where, we'll say our universal gas constant is 8.314 kilojoules per kilomole Kelvin. And our molecular weight, as we called out earlier, is 28.97 kilojoules per kilomole. Okay, many of the terms that are in here, so you say our degree entropy or our enthalpy terms, we would be pulling from table 8, as I noticed, or as I noted earlier. So we're now going to plug equation 2. So plug equation 2 into 1, and using those values that we have already called out, we're then going to say we will get results, and you need to confirm these numbers. Okay, you must confirm these values. So for Cadet Williams, we have a difference in entropy of 0.71 kilojoules per kilogram Kelvin, which then means, therefore, the rate of exergy flow is 970 kilowatts for Williams. And then we have Cadet Sanchez. Again, you need to confirm these numbers. Make sure you do them yourself. Kilojoules per kilogram Kelvin. So therefore, we have an Exergy flow rate of 1010 kilowatts. And then what would any proper CME engineer do? Double underline answer. Clearly identify what your answer is. Okay, scrolling down. So we then take those numbers, that 970 kilowatts and that 1010, and we plug them in here into system 2, or into table 2 for the system performance. Notice that table 2, if we had given this to you, would have already been populated for the energy flow rate coming into each of the 2 respective designs. Okay, so now we've got part B. We need to find the rate of Exergy destruction. Rate of Exergy destruction is a function of the rate of entropy production. So if we look back at our MC311 RDC, as we mentioned earlier, we need to determine the rate of entropy production. This is E and this is I. But if it's a one inlet, one outlet, then we could assume our inlet and outlet mass flow rates are equivalent. We could have canceled those out or left it just as consistent nomenclature. And then this statement at the end, QI E over TB, is the rate of heat transfer in relation to the boundary temperature. So say the temperature that's immediately outside of the turbine. However, we said this is adiabatic. We said the turbine is adiabatic. So there is no heat transfer. So we could then say, therefore, our Exergy destruction is equal to our mass flow rate times our dead state temperature minus the difference in our entropy at the inlet and exit of the system. Whoa, we really jumped around there. Let's call this equation 3. Okay, and then we're also going to say, and, again, using those very helpful RDC equations, we have a difference in our degree entropy terms. And this is, again, for a ideal gas with variable specific heats. Notice how we can still use this equation when we previously used it. In fact, I'm going to scroll back up here, calling out a couple things first. We have E, we have the exit of the turbine, and we have the inlet of the turbine. Notice when we used it earlier, we had the inlet of the turbine and we had the dead state. But we can use the same form of the equation for both. We can still use the same form of the equation to get an entropy difference, regardless of whether or not it's an exit or an inlet comparing across the turbine, or if it's comparing a single state in the turbine with the dead state surroundings. All right, so then we need to plug. We're going to plug 4 into 3. We're going to all use a bunch of those variables conditions that we laid out earlier in those tables. And we're going to then find that for Cadet Williams, we'll get a difference in entropy values of 0.11 kilojoules per kilogram Kelvin. So therefore, our rate of Exergy destruction is 51.5 kilowatts. And then for Cadet Sanchez, we have our difference in entropies of 0.15 kilojoules per kilogram Kelvin. And we end up with our Exergy destruction of 43.5 kilowatts. Got to remember this dot up here too because it's a rate. So there's our answer for Williams, and there's our answer for Sanchez. Something I want to call out before we move on, recall that if Exergy destruction is greater than 0, Exergy destruction is equal to 0, or Exergy destruction is less than 0, we have an irreversible process, if I can spell, irreversible. We have a reversible process. We have an impossible process. Right? So what that really means is that an irreversible process is a realistic process. That's what we would expect. That Exergy destruction should be greater than 0. And it's a good thing because we're seeing that from both of these cadets, both cadets have Exergy destruction values greater than 0, implying that both of them are realistic. So we take those numbers, 51.5 and 43.5, we plug them in down here. And we get these statements for Exergy destruction for both cadets. Now we're looking at part C. We need to do an Exergy balance. So an Exergy balance, first for rate term, we need to start out with the rate of Exergy is associated with heat transfer. Then we do the rate of Exergy associated with work, the rate of Exergy flowing into the system, and oops, I should add a plus sign there, the rate of Exergy flowing out of the system, and then last, an Exergy destruction term. Recall this deal, the negative is because of hip to win. So positive on Q because of hip to win, and negative on Exergy for work because of hip to win. Something we can call out pretty quickly though is since we have an adiabatic system, we're not going to have any Exergy transfer associated with heat transfer. So we would then say we can simplify this thing. So therefore we have Exergy associated with the rate of work is going to be simplified to this statement. Everything that's left on the right-hand side, including that Exergy destruction term, which of course has a negative in front of it, because it's always reducing the amount of work that can be achieved from any given system. Okay, tackling this, we're going to repeating the same process from part A. We'll say, but for the exit, right? So on part A, we did the inlet. You need to repeat the same process, but now for the exit. And then that will show, we'll find that Cadet Williams has Exergy at the exit of 327.6 kilowatts, and Cadet Sanchez has Exergy at the exit of 218.4 kilowatts. Okay, so now we have all the building blocks. So then we need to say, using the results for our inlet, our exit, and our destruction term. We're then going to plug it all back into this equation at the top, our Exergy balance. And we will end up with a statement that says, or we can end up with a solution that says that Cadet Williams, the amount of useful work, or the rate of useful work that can be produced is 590.67 kilowatts. And for Cadet Sanchez, the rate of useful work that can be produced is 748.13 kilowatts. Now, you need to hit the pause button. You need to hit the pause button and confirm all these numbers. Until you've confirmed those numbers, you should not move on. Okay? Agreed? Good. Glad we agreed. Okay. So, I will say that there is another way to determine this useful work, and that is the classic MC311 process. So an alternate form, alternate process for useful work. If you recall, simplification of your first law of thermodynamics. So for a turbine, if we imagine that it's going to be producing positive work, then our inlet enthalpy is going to be greater than our exit enthalpy. So we're going to have HI minus HE is then going to be equivalent to a positive work term producing positive work out, right? Hip to win. So win, we need positive work out for work to be greater than zero. Now, what you'll find is that you'll actually get results that are equivalent to this. But what the first law does not allow you to confirm is whether or not something is possible. Nor does it allow you to confirm, for instance, like is something a perpetual motion machine or the actual direction of a process, right? So the first law does not allow us to understand that heat moves from hot to cold, right? Doesn't move the other way around. And so there's very real value in understanding Exergy analysis, but I bring up this term, the difference in enthalpies, to highlight, that you can arrive at these answers actually in multiple different ways. But I want you to now see and understand Exergy balances and their utility. Okay, so taking those results, we now plug them into table 2. And we see here what we're getting. We're starting to build towards our final answers. Okay, so now we need to do part D. So for part D, we need our Exergy efficiency. And as is listed in the RDC, or the RDC list Exergy efficiency, as I'm writing here, are specific Exergy terms in the denominator. But recall that Exergy flow, let's make this an I, and in this case the I is actually not necessarily meant as an inlet, it's meant as just a sort of any given state I. So our specific Exergy is this small ex, and our overall Exergy, or total Exergy, which would say have units of kilojoules, is listed here on the left, and our specific Exergy would be, say, kilojoules per kilogram. And I should actually write this I miswrote this. It shouldn't just be kilojoules. It should be kilojoules per second, because it's a rate of energy flows. So if we take that m dot on the denominator, or in the numerator, since it's being divided in the numerator, we can end up on the bottom, and we can see how we're going to end up with a statement that is actually equivalent to, let's say, our exergetic efficiency of that turbine could then be rewritten as such. With big EX. In this case, it is actually meant to be inlet and exit. Apologies for the confusion on the nomenclature. Sometimes we always want to continue improving these things as we go forward. Sometimes nomenclature kind of gets stuck in stone, unfortunately. So then we would find that Cadet Williams has an exergetic efficiency of 91.98%, and Cadet Sanchez has an exergetic efficiency of 94.50%. Answer and answer. Okay, I would also encourage you to hit the pause button, and if you want, go figure out comparisons of isentropic efficiency and just sort of standard thermodynamic efficiency terms that you learned in MC311. Go give that a shot as well. Give that a pause. Go give it a shot. You're going to learn a lot by continuing to explore those terms and comparing with exergetic efficiency. Okay, so now we've got that plugged in down here. Table 2 is now completely filled out. We've got a good comparison across the board. We have our energy flows on the far left-hand side. We then have our exergy flows. And that's going to lead us directly into talking about the last part of this problem. And actually, I'm realizing I left an extra screen in there, so let's jump over that. So the last statement here, I'm not going to read out the entire thing to you, but this gives you an idea. So this is part E. So I will write this up here, part E. So we are comparing exergy or energy flows and exergy flows at the inlets of the two proposed designs. So comparing the exergy and energy inlet of the two proposed designs. And what we're going to find is the following. We're going to find that Williams, the energy flow rate of Williams is greater than the energy flow rate of Sanchez. So again, to be clear, this is, say, kilojoules per second. Kilojoules per second. So the rate at which energy flows into the turbine in Williams' design is larger. But the thing we now need to recognize, all right, is that, however, the exergy flow rate of Williams is going to be less, or not going to be, it is less than the exergy flow rate of Sanchez. And there's some important things to point out here as to why that is. So the reason why, well, we call this out, you'll see it down here, and the main things here is that the higher temperature and higher pressure of Sanchez's proposal ensures that you're working with, and here's the jargon that I want to stick in your mind, a higher quality energy. A higher quality energy. So Sanchez, by picking a turbine that had a higher temperature at the inlet and a higher pressure at the inlet, results in a higher exergy flow entering the turbine. And as a result of having a higher exergy flow entering the turbine, his proposal is capable of doing more work as a result, despite the fact that it has a lower mass flow rate flowing into the engine. So that's a very critical commentary. So let's close this thing out. So quick DTAMs. One, I want you to go back and review basically all of those answers, but I would say if we were to do that, we could say units are consistent, all right? So for instance, for example, if we recall your Latin, kilojoules per second is equivalent to our kilowatts, and that stays consistent throughout. I would say that we also have Exergy destruction greater than 0. Check. And the magnitude of our answers are reasonable. Okay, if you got any questions, please, you're welcome to reach out to any of the instructors, but please pour through this. You've got to practice your problems if you're going to be successful on the WPRs. All right, team, great work. Keep it up. See you next time.